Hello everyone, good afternoon. Welcome to the class ECE317 digital signal processing. Today we will keep working on the sampling process which we studied last time, right? Okay, this is a ECE317. This will be the 10th week Monday's class. Okay, for the sampling process, in time domain it works like this. Okay, we have a continuous times signal, then we take sample, then we have x of n, which is a xc of n times capital T. Capital T is a given kind of a step, right? Every capital T you will pick a value from xc and use those as the samples. And then in the frequency domain, okay, in the frequency domain, this is a Fourier transform. Fourier transform. Okay, Fourier transform. By Fourier transform, we will have capital XC of J capital omega. This is the Fourier transform of XC by continuous time Fourier transform. And this one we perform same with the Fourier transform, but it's a discrete time Fourier transform. We will have x of e to the j. I use lowercase omega. Actually, both capital and the lowercase omega, the meaning is the same for the frequency. Just we separate, use different notation. So this lowercase omega is for discrete time signal. And we have formula. These two, they are related by this formula. Okay, 1/t times the summation for k run from negative to positive infinite. And here is a capital XC of j times lowercase omega minus 2k pi over t. Now we have this formula. So if we know what is the capital XC, if we know this, then we can have the Fourier transform of the sampled signal by this formula. And I also introduce a different signal that will be used later. I put it here. That is XS of t. This one, it is summation of x of n times dirt of t minus nt for all the n's. Okay, so you can think this is a obtained from x of n, right? X of n just some numbers, and this is a signal, it's continuous time signal. But in most cases this one has value 0. Only when t equal to nt you have parse, and the parse is a xn times the parse. If you do not have xn, that's a unit parse, then you times this one, so the parse. Okay, and for this one we also have the Fourier transform. That is a capital XS of j capital omega, right? This is continuous time signals. I use capital omega for the Fourier transform for the frequency. It will be 1/t summation of k run from negative to positive infinite. Here's xc, and inside is j times omega minus 2k pi over t. Now we have this. Alright. Then we can see them in a graph way. We suppose xc of j omega looks like this one. We have an example last time, right? We have an example. In that example, xc, capital XC, looks just like this. And then the x of e to the j omega. This one is a summation of infinite terms. Okay, suppose this peak value is a. Then you need a times 1/a, right? So this one we have here will be a over t. The peak value changes, right? Here's A over T. And then we have a lot of XC. Each one is shifted XC actually, right? Shifted by 2k pi. And divide by T, we have a shift and a scale on the omega and add them totally together. So we copy these and shift to different place, right? Yeah, you do this one, you shift to different place and put them together. So the result looks like this. This is similar with this. You just make some scales by this T. And then you have another one similar with that. Another one, actually every 2 pi you have a copy of XC. Here's a negative 2 pi, you also have right, things like this. So this is X e to the j omega. This is a omega. This is a capital omega. And similar for XS, we also have the graph. It will be similar with these XS of j omega, j capital omega. But this time, you see, it is also a copy of a lot of XC. You put them together, each one shifted by 2k pi over T, and no scale on omega. So XS and XC in the omega side, no scale. So it's the same with that. So it will be same, no scale. Same with that, but here is also A over T, because you have 1 over T in the front. Same with it, and the copy were centered at every k times 2 pi over T. So you have 2 pi over T, then you have a copy, right? You have a copy, and another side negative 2 pi over T. You have another copy. Like this, right? Yeah. Okay. Then we see, we can see you when you do these things, like suppose here. What is here? Here should be pi. Here should be negative pi, and this part is coming from XC. No? Which part? You see this one. So which part will go to here? Okay, it's scaled by T. So that means this place. Here's a pi over T. This point will go to here. You times T, you will go to here. And here is also another side, negative pi over T. So this part will go to here. Will go to here. But then you see, you will have this part. This part. Right? This part. This part, the value is small, and when you calculate this capital X of e to the j omega, when you calculate this one, this part is covered by next peak, right? You have a lot of peak, you have sequence of peak value, peaks. This peak will cover this part. So this part is coming to here and is kind of covered by this peak, so you can't see it. You think it's a very small value compared with this one, but it still be there. This one will cause some, you lost some information or you change some information of a region signal. So this part we call it as alias. Alias. Yeah, it's kind of alias. It's a distortion. Distortion. So when you take sample, in the time domain, you pick some value and drop the rest values, right? You take sample, you take 1 sample, 2 sample, but between 2 samples, those values you don't keep them, right? You don't keep them, so you drop some information, you lost some information. And in frequency domain, that is the same thing, but it occurs with a different way. It's just here. This part, we call it as alias or alias distortion or aliasing. Yeah, the same meaning. So it is this part. All right, and similar here, we also have that part. Yeah, we also have that part. Then when you take sample, you will think this part as small as better, right? The aliens you don't want aliens. If you have to have aliens, you hope they are small. You have to small. So you need to choose different T to make this part small. Like here, this point will go to here, and this way. Here we do not have any scale, so this is pi over t, just pi over t. This point is just negative pi over t. Okay. So we want this part as small as better. And for certain kind of signal, we can make the sample make this part. We do not have this part. So for that kind of signal, when you take samples, you can have exactly the whole information of the original signal. You keep them. When you take sample, you will keep all the information of the original signal. You won't lose any information. You do not have these alias distortions here. That is a case I described. Actually, we need two factors for that case. First one, suppose XC of t is we call this is a band limited signal. That means XC of j omega will equal to 0 if omega absolute value larger than some omega n. And this omega n is called the limited frequency of XC of t. So you can see this is a positive omega n, this is negative omega n. For when omega is larger than this omega n or smaller than this omega n, the absolute value larger than omega n, capital XC must be 0. And between these two values, there will be something, any kind of things inside, but outside they are just 0. So for this kind of signal, we call it as a band limited signal. For this kind of signal, we can choose the sampling step t so that you see you can keep this part, right? Take example, we go back to the frequency here, XC of j omega. We can keep this part to be here. We almost keep all the information here, right? So we want this omega n inside here, inside it, right? So by that way we can keep, we will not have this part. This part is just 0. We will not have this part just 0, right? So we can choose capital T so that this pi over t will be larger than that omega n. It's pi over t larger than this omega n. Omega n is here. Omega n is here. So we want this is larger. So another word, t was smaller than pi over omega n. Yeah. So t cannot be too large. Yeah, we want some smaller t, small t. Of course, if you use very small t, that will be good. The signal, the quality of the sample data will be good. But you need a store. You need more space to store the data. But if you just choose this one, a little bit smaller than this one, that will be good. In the real application, usually people choose like a 10% less than this number. And we have name for this. We call this number as the Nyquist sampling step, or Nyquist sampling interval. Yeah, the same meaning. Alright, so this number. When you take sample, you need to choose the step t smaller than this, the Nyquist sampling step. If you choose t larger than that, you will have the alias distortion. If you choose t just equal to this one, equal to the Nyquist sampling step, then depend. For some signal it is good, for some other signal it won't be so good. Okay, and this is in the sampling step. We can also describe these t by different way. We also call like 1 over t. That is omega n over pi. This one is a Nyquist sampling rate and sample per second. That is a sample per second. Right. This is a t. T is a time interval. Every t you will take sample. Then in each second, how many sample you will have? It is just 1 over this t, right? 1 over this t. So omega n over pi. This is a Nyquist sampling rate in the unit to use the unit sampling per second. This is a similar with the Hertz. Right? Hertz is every second how many cycles of a periodic signal. Here is every second how many samples you will have when you take sample. Right? And we can also use this because this is a rate, sampling rate. You can think this is kind of frequency, right? Kind of frequency. So we times 2 pi on it. I will have 2 omega n. This is also some Nyquist sampling rate, but now is in radian per second, in the unit radian per second. All right, the same meaning. Just if you use different unit. In the SPS, you use this number. In the radian per second, you use this number, 2 omega n. So here's omega n. Right. This is a limited frequency, or frequency limit of the signal. Right. The largest frequency of this signal. This one sometimes is similar with we call it bandwidth, but bandwidth is not just for this one. We have the I just mentioned here. Like if we have a signal looks like this, the spectrum looks like this. If this is a capital XC of j omega, like this, then here this one, this is a band limit, limited frequency limit. And the distance from here, this is bandwidth. This is bandwidth. All right. And if XC j omega looks like this, this is the case. The frequency limit equal to the bandwidth. Right? Bandwidth is here. The frequency limit is also here. So this is the case. These two are same. In different paper, different books, sometimes some people think they are same, but in generally, the bandwidth, we call this as bandwidth. The band will cover the band. This kind of signal we have a lot in the real application, like a radio signal, right? Different radio channel, they cover different frequency, the channel. That each channel they have a bandwidth, they have a frequency limit, and usually people use the center of the channel as a frequency of that channel. and also like radio channels or the cell phone. Cell phone, they also have a channel. Different company, they occupy different channel. Yeah, things like that. And here, this number, the limit of the frequency, that will be important when you take sample. You will choose T. Use this one, pi over omega n. Right? If this is omega n, right? This number is omega n. Then you use pi over omega n as T, or less than that. You cannot use T larger than that. Larger than that will cause the alias. All right. Okay. Now we can see some more examples how to give the graph of the Fourier transform after you take sample. Consider the example. We consider like this. So this is the XC of J omega. Now we take sample. Use step T. Now we want to see what is the X of e to the J omega. How it looks like. Right? We will sketch it. We want to sketch it. Suppose here this is like 100 pi. This is omega, and this value it is just 1. Then what is this? Of course, depending on T, we can choose different T. Okay. We can try to use MATLAB to see how it looks like. All right. Okay. Give me a second. Alright, for this one we need functions. To run the MATLAB. Okay, this is let me see. It's still running. We want the function of these. Right. Let me write the formula here. It is x of e to the j omega or equal to 1 over t summation is xc of j. Now capital omega will be replaced by a shift and the scale shifted by omega minus 2k pi and over capital T. Right? We have this one, and k run from negative to positive infinite. So we have this formula. And this one is okay. Suppose this is just a quadratic curve, right? The square function. So we suppose xc omega equal to 0 if capital omega is larger than 100 pi, right? This is the band limited. So this is just the omega n, right? The band limit, and here will be a square. Okay, so this is a 1 minus a square, right? 1 minus omega square. But omega square, if 1 is omega square, now when this is 100 pi, it will be 0. So 1 minus omega over this 100 pi square. Okay, if omega smaller than or maybe equal to this 100 pi, then we have xc. Okay, so we need the right function. We give xc and then give x. We need 2. Alright, so let's add it. edit first one. I want XC, edit XC, this is function. I just use capital X equal to XC of W, capital omega. I don't have omega, I use W. Alright. So in MATLAB, all the variables should be a vector. So this W also a vector. We can give a list of value in capital omega. So that will be omega should be a vector. I use N and M and the size of this W. Okay, this is I needed the size, and also need X. What is X? X should be same size with W. So I use W times 0. W times 0. This gives us X. It has the same size with W. So like W has 100 values, the capital X also contains 100 values. But all the values in X now is 0. We will change it. So we know XC. XC is here. Yeah, XC is here, right? XC is here. XC is this one. It should be 1 minus this if omega is smaller than 100 pi. Right? We have this one, so I put it here. Now for I run from 1 to n times m. I write in this way. N and m, they will be size of W. Maybe it is a column vector, maybe it's a row vector. So like 10 element should be 1 times 10 the size, or 10 times 1. Now I times them together, so this gives me the whole number in omega. Alright, so for every I want xi equal to that function. I use that function. I use this function. Oh no, which one? This function. It will be 1 minus the square of capital omega I over 100 pi over 100 over pi, right? And square. So we want this, but we have a condition. We have a condition, not always equal to this number. Only if omega, if ABS of this omega, this one, it is smaller than or equal to 100 times pi. Now, if we have this condition, xi will be this value. Alright, and otherwise it will be 0. We already set x to be 0, right? So we need only change if omega I, capital omega, is smaller than this value, absolute value is smaller than this value, then we change the value of x to be this one. This is non-zero value, right? Otherwise we just keep x to be 0. Okay. Alright, we are done for this function. This is xc. Now we have xc. Then we need the second function. Yeah. What? Oh, I need to save it. Okay, just xc. Alright, this is xc. xc. xc are done. Then I need another function to show. Okay, this is a lecture for the 10th week. Which day? I said it's Monday class, right? 10 months, Monday class. Okay, lecture 10 months. You just use this. Add to these. What happened? This window, why is it so small? Sorry. Okay, I will open the new here. Put the new here. Alright. Okay, so this one I need a. First one we can see what is a xc, right? For let omega equal to. I want to see like from this one is 100, right? This is 100 pi. So 100 pi like 300. I show 500. Okay, 500 to negative 500 to 500, negative 500 to 500. I can use this one. This is omega. Then x equal to that xc of omega. And this is a figure 1. Figure 1 plot W and X. Alright, you can see what it is. XC, I need to save it, and this one I also need to save it. Now I can give the name. I call this is a lecture the 10th week, Monday's class. Okay, 10 down. Good. Okay, then I run F5, should be wrong. Press F5. Okay, so we have this curve, right? Look like this. It's a quadratic curve, and when it is over 100 pi, it's larger than 300 times pi, should be 310 something, right? It should be 0, right? This part is 0, and the other side is also 0. Okay, so this is a capital X. This is capital XC, and then we want to see what is a lowercase xc. Not lowercase xc. We want to see this one. X of e to the j omega. X of e to the j omega. I use this is discrete time, right? So I use xt for it. Xd for it. Xd. I need omega. I need different omega. Yeah. So xd. Before that, I need different omega. I use a lowercase omega or just omega d. All right. Omega d. Omega d. I run from. Actually, every 2 pi there will be one cycle, right? So I can use, for example, from negative side to positive side, I use okay, 5 to negative 5 to 5. Negative 5 with step point 1 to positive 5. I use this as omega 0. And omega d is this one times pi. Okay, so omega d, discrete one, is omega 0 times pi. Am I good? Then when I display it, I can use omega 0 as the x-axis. So that makes it clear. If divide by pi, it's like this graph, here is not so clear what kind of pi here, right? Yeah. Okay. Then I have xd. Xd, in the beginning, I just let it equal to 0, but with same size with xd. So xd times 0. I use same method. So they will have same size, the xd. And then for k run from, you see this formula is here, right? K run from negative infinity to positive infinity. I don't want so much. I just run from like a negative 5 to positive 5. Maybe more. We just see if this works, we can keep it. If this doesn't enough, I can choose some larger number. Now it's 5. For this k, xd were equal to xd plus a shifted xc, right? Shifted xc. So that is xc of j. Now is omega. Now is omega d minus 2 times k times pi, right? And over t. Oh, I don't have t. Let me give what is t now. Right? It is this one. It is one. And what is a t? We can choose different t. Okay, so first one we can just try the Nyquist one. So that will be pi over. Let me see. The Nyquist one is a pi over omega n, right? Pi over omega n. So that will be pi over omega n. Now omega n is what? It's 100 pi. Okay, just pi over 100 pi. It's 0.01. Okay, first one we choose this t. We choose this t, then we can calculate, right? Okay. So after we do the summation, we get xd. Then we can show how it looks like. This is a figure 2. And let's see, we want to plot with omega d and xd. Okay, let's run it. F5. It's here. We have, this is figure 2. This is figure 2. And this is figure 1. We can look at these two. You see? So this is original one. Figure 1 gives us the spectrum, the Fourier transform of the original signal. After we take sample with that t is 100, 1 over 100, then we have the graph looks like this. Look at this. And here's is omega d. I said I need omega 0. Sorry, I use omega 0 as a real axis. Okay, run it again. Right here. Then you see we have a sequence of peaks. Each peak is just a scale of the original one. Right, and the center, the middle one, center is 0. That means just 0. Original one. Second peak, center is 2. Here 2 means 2 pi. And the third one, here's a peak is at the 4, is 4 pi. Right? So every 2 pi we have a copy of original one. And different peak, they just touch at this point. So this is what happened for the Nyquist sample step. We use that step to take samples. You will have a sequence of the sequence of the copy of the original spectrum. For the transform, right? So we call it a spectrum, and one by one, each touch another one. They just nearby the other one. They have they touch at that point. Okay, if we choose different t, we can see now the t is 0.1. If we choose a little bit large, for example, 0.12, a little bit large. So large t, that means you have less samples, so the quality will be not good, right? And in frequency domain, what can we see? Okay, you see, looks like this. In the middle, in different, you nearby 2 peaks, right? We still have a sequence of the copies of this original peak, but at the between 2 peaks, they have a small peak. This small peak is coming from the kind of overlap. You can see. Which one? Yeah. Same like here. So when we use the t larger than the Nyquist sample step, then we will have these aliens, this part, and this side also have, and these two, this part actually, when you do summation of these two, it will cause something here. That is just the case here, you see. So in this case, some information they mixed together, right? The information, each peak contains the whole information, but in the left and right side of each peak, they have something mixed together, and it's very hard to separate them. Actually, you can't separate them. So we call this is a distortion, alias distortion. Right? It's coming from here. And if we choose some smaller t, what will happen? Right? This t is larger. If we use smaller one, like this is a 0.8, right? This is smaller one. And what will happen? They separate. You see, you still have a sequence of the copies of the original spectrum, but different copy they separate. They have gap between them. Alright, so this will be easy. This will be better. Later we should know how to restore the original signal. Actually here you can see how to restore the original signal. You just pick one peak here, right? They have a sequence of peak. You pick one. You pick one. You take one. You take one. That is just the original one. Of course, you need to do some scale. You pick one and do some scale. This is what happens in frequency domain. Then you have the frequency of this one. Then you go back by Fourier transform. You can go back. Then you have the original signal. Right? You won't lose anything. You have whole information of the original signal. Yeah. Okay, so this is one example. But the signal might be different. You know, here I use XC like this. Here I use XC like this. Maybe we can use different XC. Okay. I change the function. Alright, can you copy? And I keep these. I don't need these. Okay, I keep it. And after class, I will make a copy, upload a copy of these so you can see from the black box. Now I want a new function. Now look like this. I use different example. Yeah, this is one example. And another example. Suppose we have this. This is XC of J omega. Now here is also 100 pi, but this is 80 pi. This one is a band pass signal. We call this is a band pass signal. Band pass signal. The band waves now is here. This is the band waves. Should be 20 pi. And here the omega n. This is the limit of the frequency is still 100 pi. Then of course you can also you just think the signal cover the whole frequency from 0 to 100 pi, right? You can think like that. After 100 pi, the signal has no frequency component. Right? This part will be 0, and then you can still use this omega n. Use the Nyquist sampling step. I still use these. Is a pi over omega n, which is now is 0.01. You can still use these to take sample, and but you can also use some larger step to take sample. In this case, we just explained if you use you take sample with larger t, other than 0.01. Okay, let me write down. Do I have time? Well, you can get those data from the video, right? I don't write it. Okay, we just try this. Let me just try this. What will happen for this one? This one now the signal has two part, right? Has two part. This two part is not equal to 0, and this two part here center is 90 pi. So this is when omega, this is XC, right? XC J omega do not equal to 0 when this one minus 90 pi smaller than 10 pi, right? From 80 pi to 100 pi, center is 90 pi. The difference with these smaller than 10 pi. In this part, the signal has value. Has non-zero value. Okay, so the function here, when this one minus 90 times pi smaller than or equal to 10 pi, And we also consider the negative omega, right? So I add one more ABS here, absolute value of omega I. Then that means I consider both, right? I consider both. In this case, x will be 1 minus this omega I, but I need minus 90 times pi. I need this one, and I need a square of it. But before the square, I need to scale it. Now the span is not 100 pi, it's 10 pi, right? Okay, so I have this one. Alright, let me save it and let's run it. I still use the Nyquist sample step. Run it. Oh, what it is? I think I got something wrong. Let me see. Figure 1. Oh, why go to negative side? I got something wrong. Sorry. XC. Let me see XC. It should be 1 minus the square of these. If absolute value minus 90 pi is smaller than this one, then xi will be 1 minus this square. Think it's good? But why this is a negative value? I'm sorry, something wrong here. Let me see. X minus, I did ABS here. ABS of xi. This one. Yeah, this one also the absolute value of xi minus 90, then over this one. Okay, so I think this time will be good. Okay, this time is good. You see, figure 1 is the graph of the original Fourier transform, the continuous times case, right? We have two peaks in both sides, as I show in the paper. This one, right? I have two peaks, but here the scale, just 0 to 1. Not this, figure 1. This one, right? I have two peaks. Here's two peaks. This one and this one, right? Now it's this one and this one. Okay, and then we have summation of them. This is scale. In the y scale is like this. Maybe I can make this like this one. Yeah, looks better, right? So it is a copy of the original one. Around 0, I have 1 is here, 1 is here. Right? Can you see? My mouse here. This one and this one. This is a copy of the original one without a shift. And then shift by 2 pi. This here 2 means 2 pi, right? Shift by 4 pi, so we have all of these. And you can see they do not have overlap. The different peak, they are separate. No alias, right? And we can use some larger t actually here. For smaller t, of course, it will be good. It will be no alias. But for some larger t, for example, if I double the t, what will happen? Let's try, just try. You see, they still have some different peaks, and they do not have overlap. They do not have alias. Of course, if I change a little bit, like a 2-2. Now, if I run like this, suppose, I think they will have alias. They merge together. The different peak merge together. This is 2-2. 0.22. If I use 0.21, you see, the different peaks, they merge together, so they look strange. Each one is a merge of 2 or maybe 3 peaks together, Yeah, so they cannot separate. They merge together. Actually, I use 2.2. They also merge together just because the location of the peak is similar. I use 2.2.1. Yeah, you check the head. Here, this is not so smooth, right? And this place is also not so smooth. So actually, they something they merge together, so it looks not so good. Yeah. Then different peak they merge together. You can't separate them. All right. Yeah. But for this case, because this is a band pass signal, the original signal they have this one. The original signal, their frequency band, they have some gap between them. So you can try some larger T, larger than the Nyquist sample step, but they can still keep the sample data without alias. All right. Okay, that's all for today. Then see you next time. Okay, bye bye.